Hi there. Today we'll look at Deep Ensembles, a loss landscape perspective by Stanislav Fort, Huiyi Hu, and Balaji Lakshminarayanan. This paper on a high level explains the loss landscape of deep ensemble models, so ensembles of deep neural network. And it hypothesizes, and it shows through experiments, that each member of the ensemble, by means of being initialized at a random point, will go and, through optimization, go and end up at a different place in weight space, and therefore the deep ensemble is able to capture different modes of the functional space of the space of solutions. They compare this to Bayesian networks, which are sort of promised to do the same thing, but they often only characterize a single mode, and therefore they don't generalize as well. So join me exploring this paper. I think it's a pretty cool paper. The experiments are cleverly designed to show what they're supposed to show. And I generally enjoy this type of research because it's kind of an explanatory research that shows you what's going on inside of these networks rather than, chasing the next state-of-the-art number. It's also an example of research that you can still do while you don't have, giant resources of compute, now, even though this is by DeepMind. But I do believe that this kind of research is still, wide open and available to academia. And whereas the other kind, the state-of-the-art kind, slowly goes into more and more of the money game. All right, in any case, join me in reading this paper. If you like it, share it out, leave a comment to tell me what you think, and leave a like if you enjoyed it. All right, so we'll start off. The abstract says, deep ensembles have been empirically shown to be a promising approach for improving accuracy, uncertainty, and out-of-distribution robustness of deep learning models. So what are deep ensembles? Really quick, an ensemble model, and we're in the classification setting. So in the classification setting, we have data points, and each data point has features, so which are the x. X is some kind of d-dimensional feature, and then you have y, which is the label. So that's let's say that's some natural number or something like this, or is element of a class set. That's the complex numbers. It's element of some bounded set of class labels. So it's either a cat or a dog or whatever you want. So you have a data set of these things, and your plan is to use X to predict Y. If you build a model, a deep neural network, for example, for this task, you would simply characterize this function here. You would parameterize it as a deep neural network of many, many layers. If you build an ensemble now, what you would do is you would take the data set and simply train multiple different ones of these deep neural networks. So you'll train multiple different ones, and if you now want to classify a data point, you'll input that data point into all of these three, and at the end, you would somehow aggregate, and there are different methods of doing this, but the most obvious one is simply either to aggregate by the mean or the mode, median, whatever you want. You could also learn something here, but you can just average the predictions, and that will usually give you a better prediction than if you only have one model. So this is called an ensemble model, and if the ensemble members, these things here, are neural networks or deep networks, this is called a deep ensemble. So why do we hope to become better? That's the point of this paper is to show what happens in the loss landscape of these deep neural networks and why do they perform better than other methods that are supposed to achieve the same thing. So usually when you build an ensemble model, what are you hoping for? You're hoping to sort of learn a generalizable function. And they have this drawing right here where it's a bit of you have to sort of think differently than you usually do. So on the x-axis, you have the space of solutions. So imagine that your neural network only has a single weight. So that this axis here is that single weight. Or you can project or whatnot. This is the space of different solutions. So after you optimize, you land somewhere on this axis. And you can see that there is a solid line which represents the accuracy on the training set, and then there is a dashed line which represents the accuracy of the validation set for a given parameter. So what you usually do is you optimize one neural network to its very best training accuracy. So let's say you start off here. What you would do is you would see my training accuracy is this high. I need a different color right here, is this high. And you calculate the gradient, and you could do gradient descent, and that means you go down the loss, up the accuracy. So you go over and over and over until you reach this point right here, where you have maximum training accuracy. And then you'll suffer some generalization loss, like, so right here, it suffers some generalization loss because the validation accuracy at that point isn't as high. But generally it's correlated, as you can see by the general overlap of these two lines, of these two shapes right here. Okay, so this is called a maximum a posteriori estimate. You simply optimize one neural network until the best training error. There are different approaches right here. There are approaches that say, okay, we could do better. So first of all, what you see right here is rather peculiar, and you might not be used to this, that there are different peaks right here. There are different peaks, as you can see, in the training and the validation error. So they're correlated. And the idea is that neural networks are very nonlinear, and we've known from other papers that they have many, many local minima. And in fact, so this is one of the astounding things about neural network, most of these minima are performing equally well. So even though the neural network has different local minima, they all perform about equally well. And other papers even say they're all sort of connected on a low loss landscape. So there are many, many things that are still mysterious about neural network, but we know that there are multiple minima, and we know that we basically need to find one of them, and it doesn't really matter which one. They all perform sort of equally well. Now, as you might imagine, there are people who aren't really satisfied with this, and there are approaches to say, why don't we just capture this entire curve right here? So if we could build a model that could not only tell us at this point right here, you're this good, but could tell us that at any point, right, how good we are, capture the entire distribution of solutions. And these are usually in the category of the Bayesian neural networks. They try to capture the entire distribution. Of course, that's not really feasible because, you always have to calculate that posterior. So what they end up doing is they do some approximation. And usually they do some sort of a multivariate Gaussian approximation because you can calculate posteriors in closed form and so on. And this paper's hypothesis is that these can only usually capture one of these peaks. So they are very able to capture the surrounding right here. They can capture very accurately what happens around this particular peak. They are very aware of the shape, of the curvature here, and can tell you a lot of things about it. So they can tell you, for example, that the validation, so that you might want to be a bit over here rather than over here. But they don't generally know about these other modes because they are only approximations. They generally don't produce multimodal solutions. Another approach is a deep ensemble. Now, this paper shows that in general, if you train a deep ensemble, what will happen is because you randomly initialize the deep ensemble at some points, it will happen that if you do gradient descent on all of them, they will end up sort of covering all these different modes. They don't have an idea of, the curvature. Oh, sorry, this one shouldn't go here. This one should go here. They don't really know about the curvature, but they will give you these different minima right here. And therefore, they can capture the landscape much, much more easily. If you know that these three are minima, it might look something like this. And that's a hell of a lot better than simply the Bayesian approximation that only is able to capture one of the peaks, but really accurately. So their hypothesis here is that deep ensembles do this job of capturing the different modes of the functional space much better than the Bayesian methods, and it is why the deep ensembles work so well, because they end up in different minima. And it's a really interesting proposition. And what I find really interesting as well are the experiments that they do to show this. So they have a lot of these experiments right here. First of all, to the setup, they use CFAR10, CFAR100, and so on. And on CFAR10, you can see right here, they use a small CNN, medium CNN, and a ResNet. Now, the small and medium CNNs, their accuracy is really, really subpar. So take the results here with some grain of salt, because there are effects in these neural networks that are really qualitatively different if you are seriously underperforming, like this one. Like if you have a seriously too small network rather than a large network. Now, they do verify all of their things also with this large network, and 90% accuracy is acceptable for CFAR10. I don't think there's the big qualitative difference between 90 and 95 and so on. But the 64, if it were only this, I would be rather critical of this work. But it's fine to, if you see the effect at 64 and then some of the effects you check to carry over to the 90% one, I'm going to generally believe you. Okay, so first of all, what they do here is they look at a training trajectory of just a single run. So this paper is half about ensembles, but also half generally about what does training of neural networks do? And they reach some very, very cool conclusions that even are independent of deep ensembles. So here the first thing we do is we have some random initialization in weight space of your weight, and then you do gradient descent, and you run, right? And you get to some minima right here, some minimum right here. And then you do a second one. So you initialize somewhere else. And because you initialize somewhere else, you run, you end up at a different minimum, okay? This is a property. So these are not convex functions, right? We know about neural networks, you'll end up at different minima, but the minima, they will perform about equally well. So the question is, do those different minima that perform equally well describe the same function, or are they fundamentally different functions that just happen to reach the same accuracy? And the question is very interesting, and this paper attempts to answer that. So here you can see in the description, on the left, cosine similarity between checkpoints to measure weight space alignment along optimization trajectory. So we only consider one of these runs. Only consider the left one, for example. And you plot it here and here. This later one comes later, sorry. So you plot the left, only a single run, and you ask yourself, the checkpoint that I have after epoch 20, how similar is it to the checkpoint that I have after epoch 5? That would be right here. Now, we have to read up how they compare the checkpoints, and this is weight space alignment, okay? So weight space alignment, it basically means how much do the weights align in the cosine fashion. As you can see right here, this is simply the cosine between the weights. This is one way of comparing two functions. If two functions align in weight space, there's a decent chance that they describe the same thing. So as you can see here, as we go down the optimization trajectory, of course, each one is similar to themselves, but you can see that there is kind of a shift right here. So at the beginning, the 0th checkpoint is very dissimilar to the checkpoint at the end. But after a very short while, you kind of cross over, and then all these checkpoints right here are sort of similar. So if you just look at two rows, you look at the bottom row and you look at the top row. The bottom row tells you how similar are the checkpoints during training to the initial checkpoint. And you can see pretty quickly they are very dissimilar. So at this point right here, there is kind of a dissimilarity happening where the checkpoint goes away from its initialization to something else. And the top row tells you how similar are they to where the network ends up. And you can see that there appears to be a period in, let's say here, where this shift away starts, up until here, where it's kind of not similar to anything. But then after that, after here, everything is similar to the final checkpoint. Okay, so this is sort of tells us a hypothesis is that you initialize randomly somewhere. You have this loss landscape, right? You initialize randomly somewhere here, and then you go, and at some point you fall into one of those valleys, and then you simply go to that valley. If you initialize somewhere differently, you can see that at the beginning you might be here somewhere, and then you fall into that valley over here. And after that, you're pretty much set. So this is going to be our hypothesis from now on, that in these neural networks, the initialization is basically you are somewhere and you kind of meander around a bit until you happen to go into one of these directions, which happens pretty quickly, and then you fall into a hole basically, and that's rather convex setting in that thing. Okay, a really interesting thing that they do is that they check the disagreement of predictions. So you might think that if a neural network achieves 65 or 90, let's call it 90% accuracy on C410, right? That there are just, they're this data set, that's 100%, and there are just these 10% over here that are just the hardest, right? And the more you train, the more you're able to push this boundary to the right. So if you train more, if you have a better network, you're just able to explain more and more of the samples. However, this experiment here is going to show that this is not the case. What they measure is the disagreement in predictions, which basically means that there is this data set, the validation data set, and if I have one random initialization and I train it to 90% accuracy, it will say these, it will not be able to classify these here. But if I have the same network, but a different initialization, it might not be able to classify these over here, but will be perfectly able to classify these over here, right? This is also very interesting property. And you can see right here the disagreement of predictions as you go through the training. So again, we're going to look at the bottom and the top row. So the bottom row and the top row. Red is very disagreeing, blue is very agreeing. You can see again that I introduced the different runs. I'm already taking this away from later. We are just looking at one single run for now. This is a result that's going to come up later when we look at two different runs of the same neural network, and that's the astounding part. Okay, here we're just going to look at one run again during training. So we can see right here at the beginning, of course, every checkpoint agrees with itself on the predictions. However, you can see that pretty quickly the checkpoints start disagreeing. Very quickly, everything is red right here. However, on the top, you can see how much do these checkpoints agree with the end, with the 30th epoch checkpoint. You can see that there's a period that is red, right, from here to, let's say, here. And then after that, they all start agreeing. So from here on out, it's all pretty blue, which basically means that that they agree with the last checkpoint. So that all of these agree with the end of the training. Again, this is our hypothesis here, that once you're in this valley, that the function kind of stays the same and you only sort of micro-optimize the function. However, at the beginning, you decide into which of those valleys you want to go. And the different initializations will lead you to different valleys. And that's what they show right here. So they do a t-SNE plot of predictions. t-SNE is a method to down project high dimensional vectors. And This is the weight space projected to 2 dimensions, so t's in the axis 1 and 2. These are rather arbitrary. It's just if you think of a PCA, it's the directions of maximum variance. And you can see the 3 different runs, they immediately at the beginning right here, they immediately go, you can see they do large distances at the beginning between the steps of optimization, and they do in very different directions just by means of being initialized at different points and having maybe a bit of noise in the training process. But once they are at the particular location, they sort of just kind of bounce around right here and try to find the best minima in that region. So this is our first indication that if we train the same network multiple times with random initializations, it's going to end up at different places. And what we're wondering is, we already know that a single network is very different at the end than at the beginning of training. What we want to know is, are 2 networks also very different even though they're trained on the same objective? Just because they are at different places in the weight space doesn't mean they are functionally that different. There are symmetries. And it's going to turn out, yes, they actually are very, very different. So this is right here. Here you can see 2 different things. And we're going to read the plot along with it, just so I remember what I'm seeing here. So using 2 different architectures, okay. For each of these architectures, the left subplot shows the cosine similarity between the different solution weight space, and the right subplot shows the fraction of labels on which the predictions from different solutions disagree. Okay, so it's the same as before. The left is the alignment, and now it's not during training. Now we restart independently. We train the same network 10 different times, and after that, we're going to compare the 10 different solutions. Remember, these all achieve roughly the same accuracy on the data sets. And this is the same whether you go to a big architecture like this ResNet 20 or to a small architecture like this small CNN right here. You can see that every single solution, of course, agrees a lot with itself. That's the diagonal right here. But it's not a line, it's completely orthogonal to all the other solutions. So all the solutions in weight space are orthogonal. Now there's still a chance that there's some symmetry in weight space because if I have a neural network, I can just exchange the connections, and if I also exchange the neurons, then it will be the same function. However, you can see right here that they completely disagree. So this small CNN, remember, it had like a 65% accuracy. The solutions, the red here, they disagree on 25% of the labels. So that this is exactly this effect we saw before. We train one solution and it will not be able to classify these parts of the validation data set. And we train the same network with the same data set, with the same loss, with everything the same. Again, just from a random initialization that's different, it will end up performing equally well, but it will make the mistakes on an entirely different set of the validation data points. Like, this is rather astounding, I feel, because I think most people are of the idea that the kind of data points have an intrinsic hardness, and if we get to 70% accuracy, it will always be the same 70% of data points that we that we correctly classify. This is not the case. And this is one thing I think this paper and this line of research does pretty cool, is to look at these networks in terms of their prediction agreement. So they go further and they compare this to 4 different methods. So they say, okay, ensembles are one method of kind of getting different solutions, which means we start from random initializations. But there are other ones. So for example, there is, just place this correctly here, random subspace sampling. So what does it mean? We start at an optimized solution. So you train a network, one single network, and then we choose a random direction at v in weight space. We step in that direction by choosing different values of t, looking at the predictions at configurations theta 0 plus tv. We repeat this for many different v, but always the same theta 0. So in our original kind of drawing of this thing, we optimize one single network. Let's say that's here. And then we sort of wiggle around in here into different random directions. Now, of course, there's only one random direction right here. If maybe we can look at this at the, so if here we have the loss landscape, and maybe over here there is a bit of a thing, and over here there is a bit of a thing. You thought I was gonna draw. Okay, so we start here, and maybe that converges to somewhere here. So what we're going to do is we're going to select random directions in that space, and we're just going to go a few steps into this direction and then compare the weights. Now here, you can already see by the way I'm drawing it that this will probably make you stay in the same region. And our hope with ensembles is, of course, is that they are able to capture all of the three different modes right here. But it is a way to obtain different solutions that all also perform quite well. If you only perturb your solution by a little bit, it also works quite well. And you can build an ensemble out of these methods right here. You can build an ensemble out of these. In fact, these Bayesian methods, if you do these approximations with Gaussians, that's pretty much what they will end up doing, is they will end up characterizing the local landscape around one of these minima. But here we simply do it by randomly stepping into a direction. That's the first method that we're going to investigate to obtain an ensemble of different solutions. So deep ensembles means we randomly initialize many times and then train from scratch each member. This method here means we start from a solution and we simply perturb it into random directions. The next thing we can do is we can do dropout, subspace dropout. We again start at an optimized solution, apply dropout with randomly chosen probability. Again, our hypothesis is going to be that this is going to keep the network rather in the sort of same kind of functional mode and not switch over. Diagonal Gaussian subspace, again, we start from an optimized solution. You see the pattern, and here we actually do some sort of a Gaussian approximation to the functional space. We calculate a mean and a standard deviation, and we draw samples of the parameters from that distribution, and then the same in a low rank regime. And here you see what happens. So here is these things. For example, the random subspaces. Here is this overlapped with the plot we saw before. So here we have three different trajectories of runs, and then at the end of each trajectory we take the best solution and we do this random exploration around it. And this here is the t-SNE projection. Now this isn't, I have to say, this isn't the projection of the weights itself. Sorry, I did not say that before. This is a projection of the predictions, I believe, of a subset of data points. So this is the prediction projection of that. And you can see that if we perturb the solutions like this, all of these solutions, all of these ensembles, they stay in their basin of attraction, as you can see right here. So with a deep ensemble, we would build an ensemble that we would build an ensemble that combines this point and this point and this point. Whereas here we will simply either build an ensemble that combines points in here, or we'll build an ensemble that combines points in here, and so on. And you'll see this for all the different methods that we consider here, especially the Gaussian methods. And that's a hint to why, even though Bayesian networks explicitly try to capture the entire distribution right here, what they'll end up doing is they'll simply end up capturing a single mode. And that's important because the single mode is always functionally sort of equal. We saw that this is a training the trajectory, And at the end of training, after like this step right here, all the functions are pretty much the same, right? They pretty much agree with the end optimum. Whereas between the runs, these functions completely disagree with each other. So it is important, if we want to build an ensemble, to capture as many of these modes as possible, and only the deep ensembles can do that so far. So this is another experiment where they show this loss landscape, and I really like these kind of plots. So what you see here is a plane. It's a 2D plane, and the 2D plane is described by 3 points. So one point is the origin. You see right here, the origin. That's the origin that's the 0 in weight space. Okay. Then what you have are the 2 optima. So you run an optimization 2 different times. Once it's initialized here, and it runs to here, and once it's initialized here, and it runs to here. Okay. So that defines the plane that we're going to look at. Now, for each single pixel in this plane, or actually for each single pixel in this half circle right here, they evaluated the networks. So what you'll do is simply you do linear combination of the weight vector here at this optimum, the weight vector here at this optimum, and you can, for each point here, defines a neural network with those weights, right? And you can evaluate it. And that's what you get. This is the accuracy of the neural network at that point. So here you can see very, very clearly that there are these 2 different modes right here. So even though they're initialized super close to each other, right? You can see this right here. They're initialized super close to each other because this is the flat area right here that we saw before. Because they are in the flat area, even though they're initialized pretty close, the red one is a little bit more to this basin of attraction. The blue one is a little bit more to this basin of attraction. So they move over, and as soon as they're in, it's like boom, they go to the minimum of that basin. And this area is rather convex, and this area is rather convex. And in the middle, you can see is more loss. So no solution will go there. That's how you get these different minima. That's how you get these different modes. And you can see the accuracy from the color is going to be the same in each of the valleys, consistent with what we know so far. Now here, the pink stripe is a Gaussian exploration. So if you now do a Gaussian perturbation, Gaussian exploration around this minimum, you can see again, you don't get out of this valley. You're not going to go to different modes. The weight space is just too large, and you're going to simply be stuck in there. So the only chance almost you have is to initialize again and hope that you end up in a different place. And I guess my hypothesis is that there are many, many more of these valleys, of these basins than that you could ever capture. So basically every single initialization that is different will lead you to a different one of these basins. I guess it's only a matter of this size. So here again, they do a function similarity. So in this case, it's the function similarity to optimum 1. And this is again how many of the labels agree with the optimum right here. And you can see that within this basin of attraction, you have fairly high overlap of the functional similarity. But here, none, right? So 15% or so. It's not going to be 0 because they're going to agree on like some of the examples. I guess there's still something like intrinsic hardness, but they agree on almost none of the labels. At least, I guess, if you normalize by their base accuracy. So even though optimum 2 is performing as well, it is functionally extremely dissimilar to optimum 1. So these describe really different functions. And I really don't know what to make of this other than, each one of these is maybe sort of deciding to look at different features in the data set, right? Or to maybe build different high-level features from the same low-level features. And maybe we're still under-parameterizing these models because not a single model can sort of look at both features at the same time, as evidenced by the fact that each of these is always going to one of these things. Or it could be that in fact the task is way too simple and it can be solved in like 500 different ways, and each of these optima is simply one way of solving the task, one way of combining a feature, and it's actually completely an overspecified problem. That's another hypothesis. It would be, I guess, interesting to look at these things, and I'm sure there's work on this. So you can see the same thing for optimum 2 right here, where, okay, go away, where you can see that optimum 1, it agrees almost nothing with optimum 2, right? It doesn't agree. There's not even a hint of a valley right here in the terms of functional similarity. That is very, very interesting. So it really means that these two things describe two different functions. They do these other plots right here that they call diversity versus accuracy plots. So what they'll do is they are going to have different models, and they're going to look at them in terms of their diversity and their accuracy. So here the y-axis is going to be how different are these functions. And that's going to be, again, in fraction of labels changed, normalized by the base accuracy. So here you can see we always start from this baseline optimum. This baseline optimum has zero diversity, zero, because it agrees with itself on all the different labels, of course. And then we're going to disturb that using our 4 methods that we defined before. So we're going to randomly subspace, we're going to drop out, we're going to Gaussian perturb it, and so on. And the more we perturb it, the more diverse our function is going to be, naturally, right? Because we perturb the function, it starts disagreeing more and more and more with our original optimum. However, what we also expect is, if we are in the local optimum and maybe here, and maybe the validation accuracy is sort of beside it or a little bit larger and so on. So if we perturb it a little bit, that might not make too much to our accuracy. But if we perturb it a lot, we go actually up the loss landscape, and then we get less accuracy also on the validation set. So that's what you see right here in this curve right here. As you make the function more diverse, so you perturb it a little bit, you see that your accuracy doesn't suffer too much. You kind of stay at the same accuracy, but as if you make it more and more and more diverse, you can see that the accuracy suffers until the diversity of 1 basically means that you disagree on the maximum amount of labels that you can. And so you're sort of out of this valley right here. And also, you can see that your accuracy goes to 0. So the more these functions disagree, the less their accuracy is. That seems natural. However, you can see that these red stars right here, they seem to be also very different. They seem to not agree with the original baseline optimum, but they seem to be doing perfectly fine in terms of accuracy, be at the same accuracy. And those are the independent optima. Those are the optima from runs where we initialized at a different point and then also trained. And that, again, is evidence for the fact that there are probably other optima far away where these different initializations find this here. So they are very different in terms of functional space. They're quite far apart. They predict different things. However, in terms of loss, they're almost the same, or actually the same. So this is very, very cool experiments right here. And they do this for the different architectures. And you can see that, especially the larger architectures, this actually happens more pronounced. And they also make the point of saying, if you go to harder problems like a CFAR 100 or an ImageNet, this effect is more pronounced, that you can see these here are closer together as a curve. and these are the independent optima. So I hope you're already on board and still know why we're doing these things. We're doing these things because we want to build some sort of ensemble that captures the distribution of solutions in order to generalize better. Now we have two options. Either we start kind of from an optimum and characterize the space around that optimum, which is what these methods do right here, and what also the Bayesian methods do this, even though they don't want to, because they do these approximations, because they're intractable, they're going to end up doing this. Or our other option is to restart training a bunch of times, and then we end up at different optima. And the point of the paper is it's better to do that than to build the ensemble out of these Gaussian methods or of these perturbation methods. And the paper, I guess the main claim of the paper is why that happens. And it happens because the ensemble members obtain different minima that are functionally different. Okay, so exactly, that's what they do here. So they now build ensembles out of these different things, and you can see that here on the x-axis you have the ensemble size. So how many ensemble members do you have? And the dashed lines here are the baseline accuracies if you just have a single model. And the test accuracy is plotted on the y-axis. Now I actually was not, that's not correct. You always build the ensemble out of random initializations, but on top of that you do these things. So what you can see right here is if I have this classifier, which is my original classifier, and I add on top of that this PCA Gaussian perturbation stuff, I increase in accuracy. Okay. However, if I build an ensemble, I increase in accuracy. If I build an ensemble out of 10 members, I increase in accuracy this much. Okay, and then because I can do both things. So if I do an ensemble and then on top of that do the PCA Gauss, I gain another this much right here. So that's sort of evidence for the fact that you'd rather build an ensemble than do this these other methods of approximating the Bayesian posterior of weights. So yes, I'm sort of convinced. I hope you are too. And they do some more experiments right here where you can see that the difference between, so this is this is I guess here accuracy. Oh yeah, this is the out of distribution test. So you can take a data set and you can corrupt it by corruptions. So there are predefined data sets, but you can also do it yourself. You crop it, you can do luminosity, whatever. You can destroy parts of the image. You can see that having more ensemble members, so this is your original models. Here is how they sync with increasing corruption. It almost doesn't matter which ones of these methods you do. You see the bottom one is the original model, and you gain a little bit by doing these things, but not nearly as much by building an ensemble and going here, or actually an ensemble of 2 members or of 5 members, in which case you jump this much in accuracy. So these ensembles from different initializations are also very good at countering corruption, which you see also here. Yeah, so this is the JS divergence. Okay, I've read that, but let's not go here. Video's already too long. And this is the last thing, is on ImageNet test set and the ImageNet corrupted set, where they pretty much show the same thing. It's not as pronounced here, but you can see pretty much how if you go from single model to ensemble with 2 members to ensemble with 4 members, there is a general upwards trend, and the general upwards trend is much less pronounced within each ensemble. So if you just go from method to method, than it is between the different groups of ensembles, meaning that the ensemble is a much more pronounced effect than these other effects. So I hope I have convinced you a little bit of how these subspaces look like, how the loss landscape of neural networks look like, especially the fact that there are these different minima, and the random initializations will almost always hit these different minima. And the interesting part is that even though these different minima perform equally well, they are functionally very different. And an ensemble of differently initialized and independently optimized models can actually capture these different modes of the functional space. And therefore, if you build an ensemble out of that, it will generalize better because it kind of can draw information from all of those different modes, rather than if you do some sort of Bayesian network, which will, because you have to approximate usually with Gaussians, will end up only covering one of these modes. That is sort of a good summary of what this paper says. I enjoy research like this because it's easy and it kind of makes you think, right? So I'll be thinking about these things for a while now and thinking of new kind of experiments that one could do. And yeah, as I said, this research is still wide open. We don't know so many things about neural network. And, tell me what you think is going on, actually. That would be very interesting. And yeah, I'll see you next time. Bye-bye.